So as you go through it, you're trying to figure out what formula in order to come up with. There's one main one. It's that y equals a times b to the x. That's the main formula for exponential growth and decay. Okay? The only other options are the ones that are on the front page of, are the money ones. Okay? If you're working with money in compounding, then it's either the PERT formula or the other money formula. PERT formula is when it's compounded continuously. If it's not compounded continuously, then it's the other one. Those are the only three that you have. Okay? So most of the time, it's going to be y equals a times b to the x. Unless it's money. Okay? On number 4, here's the clarification I needed to make. So they go through and they talk about population in Reno, Nevada. It says population P in terms of thousands, which we'll talk about in a second. That's a subtle thing that changes the problem, okay, that you have to be aware of. And they gave you this P of T, or P of T equation, where T is the year, starting with 1990, and in 2000 the population was 180,000. In part A, they asked you to find the value of K for the model. Here's what I actually want you to do. This is what I meant to remind you of yesterday. They're basically saying in part A, find the equation that models this problem. I don't necessarily want you to do it with base E, because we haven't done anything with that. I want you to do it in y equals a times b to the x form. Okay? Just like we've done every other problem, just like we've worked on. So as you work your way through that, here's a couple of things we have to clarify. The 134 that is in this part, that is the A value. That's your initial value. That's your population of Reno, Nevada in 1990. That's what that 134 is representing. But here's one of the things I said is subtle but changes the problem dramatically. Did Reno, Nevada have a population of 134 people in 1990? 134,000. That's where it says the population P in thousands. That 134 is representing 134,000 people. Okay? So when you're going through and you're writing this equation, we know we've got the A value of 134. We know we're going to look for the B value. We got to figure out what's the multiplier then after 1990. And they gave you some more information. They gave you that extra point to plug in. They said in 2000 the population was 180,000. Well, in 2000, that's 10 years later, so that means X is 10. What do I plug in for Y? 180, not 180,000. That again, that's that subtle difference. 180. Okay. What's that? In the first part, in the first line of the problem, it says the population P in thousands. So that's how they're defining it, is in terms of thousands of people. So whatever number, you got to throw thousands at the end. 180,000. 134,000 people. So now we solve for B. 2 steps. Divide both sides by 134. And then I don't want B to the 10th, I want B. So how do I get rid of the 10th power? We take the 10th root, which is the 1/10th power. So we would go through and raise this to the 1/10th power, and that'll give you B. Which, based on the answers I gave you, should come out to be about 1.03. So here's your actual answer to part A. There's the equation that's actually modeling this. Starting value of 134,000 people, and then a multiplier of 1.3. There's your exponential growth, your rate of growth. And now in part B, they ask you, use that model to predict the population in 2020, which is 30 years later. Therefore, all you have to do now is just plug in 30 and get an answer. Okay? Plug 30 in and get an answer. Make more sense now, hopefully? Like I said, my bad as I was trying to get you all of the different stuff at the end and rush through it, I forgot one thing, and this is what I forgot, is to clarify. Don't use that formula, do it the way you've normally done it. Okay, finding A and B. Okay. Like I said, if you have any other questions, I'm going to have you hang on to them for now, and I'll answer those individually then during work time if you have some you want me to clarify. Otherwise, here's what your test is going to look like. Okay, day 1 of your test. Here's some examples. We're going to run through these fairly quickly. Here's the non-calculator part. Okay, everything we do right now is no calculator. So put that aside so that you're practicing without a calculator. On day 1, there's basically three concepts, and we kind of put each concept on a page. So here's page 1 of your test, something that looks just like this. Different problems, obviously, but same type of problems. Here we go. Problem number 1. What's the answer? 1/2. Why 1/2? Okay, remember what a log is asking you. 9 to what power gives you 3? The 1/2, because remember that's the square root. 1/2 power is the square root. So 9 to the 1/2 power will give you 3. Okay? Here's your first problem. Number 2. -2. Okay? What the problem's asking you. 4 raised to what power gives you 1/16? Well, 4 squared gives you 16. By making that negative, that's what drops the 16 into the denominator. Remember, a negative exponent turns it into a fraction. Drops the answer into the denominator. So this one is -2. 4 to the negative second power gives you 1/16. How about number 3? Now, 1, you might just be able to look at it. It's the exponent. If not, you might need to work with it a little bit. We can always bring the exponent out front. So you could rewrite it this way. And what's the natural log of e? 1. E to what power equals e? Remember, that's what natural log of e is asking you. E to what power gives you e? E to the first power. So this is just 1 times the -3. Means you get -3. Okay. Same idea on 4. What's the answer on number 4? It's not 3. 6. If we do kind of the same thing, bring the 3 out front. 3 times the log of 100. What's the log of 100? Nope. 2. Remember, power. 10 to what power gives you 100? 10 squared. So this is 2. Okay, the log of 100 is 2. 10 squared. And then 3 times 2 gives you 6. Okay. Now, keep in mind, I'm going pretty quickly right now. Okay? Because some people are getting it right away. Some people are struggling a little bit. But I say that because you're going to have plenty of time on the test on Monday. You're not going to be rushed for time. Okay? You'll have plenty of time as you work your way through. So it's not like it's a race of, all right, let's see how fast I can get through this first page. We're going fairly quickly because, like I said, some people are getting it right away. And I want to give you a chance to have some work time. But you'll have time to think it through. Okay? You'll have time to stop and say, all right, let me think about this for a second. You don't have to, it's not a race. Let's go to number 5 then. Last one here on these types of problems. The last type of example that you saw with this, we just took the log of each part and then added the answers. Unfortunately, 6 to some power, there's not a nice power that gives you 54. So we got to go a different route. I can't get a nice answer for both of these. So what do you think? What's another option? Somebody said it. Condense. We're adding 2 logs together, which means I can condense those into 1 and then evaluate the answer. So log base 6. When we're adding 2 logs together, what do? Multiply the arguments. So 54 times 4. Okay. You can do this in your head. 54 times 2 is 108. And then you double that and you get 216. Okay? You get no calculator whatsoever. Okay? Now, hold that thought. That's because that's a good question. So the question then, the next question is, are we supposed to know what 6 to what power gives you 216? You might, on the test, these numbers wouldn't be as big. Okay, just as a heads up. The one here is a little bit big. Anybody know? What is it? 6 to what power gives you 216? Third. Yep, you get 3. Like I said, the ones on the test don't have quite as big a numbers. Okay? They don't have quite as big a numbers. Now, let me tell you this too, by the way. As you get in and you look at a problem like this and you start, a little bit of the panic mode starts to set in. Well, how am I supposed to know what 6 to what power is 216? Can you do 6 times 6? Yeah. Can you take 36 and multiply by 6? And then you get, so you can multiply, it's okay. You know it's got to be 6 to some power, so just multiply by 6 if you can't think of it. If it was 5 to a power, start multiplying by 5. 5 times 5 is 25. Times 5 gives you 125. Times 5 again. Just you can multiply. You can handle it. Don't go into panic mode of, I don't know what this is. Work your way through it. You'll be okay. Okay? Here's page 1 of your test right here. This is it. There's about 6 or 7 of them, I think, on page 1. But this is it right here. Okay? So there's the first type of problems. Second type, graphing. Let's go back over some graphing stuff. All right. On the test, as we graph, I'm going to go over one exponential and one logarithmic graph today. There are 2 of each on the test. There's 2 exponential and 2 logarithmic. Okay? Again, before we go into panic mode, relax, take a breath, and let's take a look at what this is like. Okay? First one, exponential. Is this going to be exponential growth or decay? Growth, because the base is bigger than 1. Which means, here's why I say this is going to be so much easier for you. There's your parent function right over there on the wall. All you have to do is take that graph and shift it based on whatever you're looking at. All you have to do is take that graph that's on the wall and move it around based on the equation you're working with. Okay? Now, there's 2 main features of an exponential graph. The y-intercept is at 0, 1. That's your starting point. And you've got a horizontal asymptote at y equals 0. Those 2 things need to be shifted, and then you sketch the rest. So normally, I would have a point right here. What is the minus 4 going to do to the graph? 4 to the right. And what's the plus 2? Yeah. So everything, that graph that's on the wall is going 4 to the right and 2 up. That's it. So I take this point. Let's go 4 to the right. 1, 2, 3, 4. We'll go up 2. There it is. Okay. The horizontal asymptote is normally at y equals 0. Well, it doesn't matter whether I shift that left or right. It's still at y equals 0. But it does matter that I moved it up 2. So now my horizontal asymptote is right here. Went from 0 to 2. And we already said this is exponential growth. So now I can sketch the graph, and it's going to look something like that. Okay. There's the sketch of the graph right there. Now, I put this stuff over here because this is what you're going to be asked on the test. This is exactly the stuff that you're going to be asked on the test. There are these 6 pieces. So let's identify. Vertical asymptote. We don't have one. Logarithmic graphs have vertical asymptotes. Exponential ones have horizontal. Okay? So in this case, vertical, none. Horizontal, where to go? 2. Yeah. Normally is at y equals 0, but we moved it up 2. Y equals 2. Domain of all exponential graphs. All real numbers. Range of this graph. 2 to infinity, not including 2. Everything above the horizontal asymptote. 2 to infinity. X-intercept? None. There isn't one. Because that graph got moved up, okay, most of the time there won't be one. None? And how about a y-intercept? Oh. This one's a little bit tricky. Y-intercept is when? In general? X equals 0. Plug in 0. If I plug 0 into the equation, I get -4. What's 3 to the -4th power? Here we go again. Here's that multiplying by 3. 1 over 81. 3 times 3 is 9. That's 2. That's squared. Times 3 is 27. That's 3. Times 3 is 81. So 3 to the -4th power is 1 over 81 plus 2. 2 and 181st. Okay? Y-intercept, 2 and 181st. And there it is. Hey, will you guys focus?
Yeah, distracted.
There's people trying to focus and you're screwing around back there. Okay? But y-intercept, like I said, is when x equals 0. Plug in 0 and get an answer. That's where this came from. Okay? There's your exponential graphing right there. Just shifting it left, right, up, down, and then evaluating from there. Okay? Let's go to logarithmic. Let's do one of those. So there's 2 exponential graphs on the test. And again, there's your parent function right over there on the logarithmic one. Okay, it's right next to the exponential graph. And again, I'm not going to take those down. I'm not going to cover them up. That's too much work. They're there. Use them. Okay? Use them. All right. So, a logarithmic graph, like I said, kind of parent function over there. So since 0, 1 was the y-intercept originally, because we know they're inverses, that means 1, 0. This is normally the starting point right there. And normally the graph looks like what's on the wall. Now we're going to shift it. What's the plus 1 do? Going to the left 1 and up 2. Left 1, up 2. There's the new starting point right there. The other part, remember you've got a point and an asymptote that have to be shifted. On logarithmic graphs, you would normally at x equals 0, you have a vertical asymptote. But because we're shifting it to the left one, the asymptote goes with it. So normally it's the y-axis, but we shifted everything to the left one. And therefore, there's the new vertical asymptote. You also know, since this is base 3, we basically have logarithmic growth. So it is going to look just like that. So we sketch it in. There's your sketch of your logarithmic graph right there. All right, let's fill out the information that's going to go with it now. Vertical asymptote at x equals -1. Yep. Horizontal asymptote. We don't have one because it's logarithmic, not exponential. None. Domain. Everything to the right of -1. Okay? -1 to infinity. Another option, by the way, just as a heads up on domain for these in particular, if you don't like just looking at the graph, remember you can't take the log of a negative number, which means the argument has to be positive. So it's got to be bigger than -1. That's another way of thinking about it if you're looking at a log equation. You got to have a number bigger than -1 so that that's positive. How about range? All real numbers. Good. -infinity to infinity. All right, and then we get to X-intercepts and Y-intercepts. And in this case, we have both. X-intercept is when what is true? When y equals 0. So we're going to take this equation. We're going to set it equal to 0, and I need to solve for x. We're right back, though, to what we've been doing all week. You're solving a logarithmic equation, just like we've been working on for the last 2 or 3 days. Which means, remember step 1 we've talked about the last 2 days? Isolate. Get the log by itself. Which means that plus 2, we got to subtract it over. We got to get rid of that. So we're going to have log base 3 of x plus 1 equal to -2. Now that the log is by itself, switch forms. Change it into exponential form. Okay? Once you isolate, then you change forms, always. So in this case, we start with base 3. 3 to what power? -2 equal to x plus 1. And then solve from there. Okay? What's 3 to the -2nd power? Yeah, 3 squared is 9. 3 to the -2nd drops that 9 to the denominator. 1/9 equal to x plus 1. Subtract the 1 over, and we get negative 8/9 as our x-intercept. 1/9 minus 1. Okay. 1/9, when you subtract the 1 over, we get negative 8/9. Okay. So, which is about right there on our graph. Okay. But in that case, you do actually have to set it equal to 0 and solve for x to find the x-intercept. Okay. Last part, and this one is easy because it's on the graph. The y-intercept is 2. It happens to be the point we shifted, but that's not usually the case. So let's kind of go through the solving of that as well. Y-intercept is when x equals 0. We said that already. So if I plug 0 in, we would have the log base 3. If I plug 0 in, my argument is 1. And then we have a plus 2. I need an answer. What's the log base 3 of 1? Nope.
0.
0. Remember what this says. Think back. Let me bring you back here as you try to answer that question. Remember what this is asking. 3 to what power gives you 1? 3, what would you raise? So when you say 3 to the third power doesn't equal 1. If you said, I heard 1 out there from somewhere as well. 3 to the first power doesn't give you 1. Okay? So as you're thinking, that's what you should be thinking when you're evaluating logs. Okay? 3 to what power gives me in this case 1. So that's 0 plus the 2 that's already there confirms what we already knew because it was on this graph in particular. Y-intercept is 2. Like I said, most of the time you're not going to actually have the point on the y-intercept, so you will actually have to find it. Okay. There's graphing. 2 log problems, 2 exponential problems. Okay? Which is why I said, before you panic, I know we haven't done these in a while. Okay? We did them earlier in the chapter and then haven't done them in a while. Before you panic, they're doable. Okay? You can handle this. And the last page of the test, then here's the last type of problems you're going to see on Monday. Some solving problems. A couple of solving exponential equations without a calculator. A couple of solving logarithmic ones without a calculator. Okay. And we'll go through, like I said, we'll go through 2 problems, and then I'll give you the reviews and give you some practice time and question time. All right. So you might look at this and say, how am I going to solve that without a calculator? Here's the number one part you need to be able to do. Okay? We've already got the base by itself. It's already isolated. Which means what you need to be able to see. This is what you need to be able to do. 1/2 and 32 are both powers of what? 2. They're both powers of 2. 2 to what power is a half? This is really just 2 to the negative first power, which is then raised to the x. 2 to what power is 32? Close. Turns out to be 5. And again, if you're not sure off the top of your head, just multiply by 2 until you get there. Okay? Power to a power, we multiply the exponents. 2 to the negative x equals 2 to the 5th. And once the bases are equal, all you got to do now is focus on the exponents. Negative x has to equal 5, which means what does x equal? -5. Yep, there's your answer. X equals -5. Okay. But the key part to solving these problems by hand, got to have the same base. You got to figure out what base do we have here, and then work your way through. Eventually, once you get the same base, then you can focus on the exponent instead. Let me give you one more. And then I'll let you work. So again, you probably look at this and your instinct probably kicks in of, how the heck am I going to do this one by hand? Again, back off the panic mode. That's step number 1. And like I said, let's isolate the base. Let's start there. So, what's the first step then? Divide both sides by 2. So if I divide by 2, we have 1/3 raised to the x over 5 equal to 27. Okay, 54 divided by 2. Now you're right back to where we were. 1/3 and 27 are both powers of what? 3. So we rewrite these with base 3. 1/3 is 3 to the negative first power. 27 is 3 to the third. And now we clean it up just a little bit. Again, power to a power, we multiply those exponents. So I've got 3 to the negative x over 5 power equal to 3 to the third power. And once the bases are the same, now you can focus just on the exponents. That means the exponents have to be equal. Negative x over 5 has to equal 3 in order for those two to be equal. And we solve from there. Multiply both sides by 5, which means x equals negative 15. Okay. What's that? You could. And actually, that's a good question. Somebody asked me in one of the other classes on one of the review problems. Somebody asked, if I see it, can I just put the answer down? And the short answer is absolutely. Like if you look right here and you're thinking, oh, I know what this is, go ahead and answer it. It's fine. The only thing I cautioned him on was, if for some reason you make a mistake and you have 0 work, I can't give you any partial credit. Now, if you don't make a mistake, then you're fine. Okay? So that's the only thing I would caution you on is, if you're confident and you're like, yeah, I know this is right, okay, then write it down and put the answer down. But if you're wrong, then you get no credit at all. Okay? So just as a heads up on that one. What we just did is almost the entire test. That's it, right there. That's the whole thing. Okay? There's 4 solving problems, there's 4 graphing problems, and 6 or 7 of those first ones with log problems. That's it. That's all there is. Okay? So you should know now kind of exactly what you need to know for Monday. Exactly what you're expected to know. And then, like I said, Tuesday are application problems and solving harder equations, okay, where you need a calculator. Let me hand out the review.